3y squared. Well, in this case, for z equals c, we get an ellipse with semi-axes in the same ratio, but with the square root of 3 over 3 and square root of 2 over 2 both multiplied by c to the 3 halves. Now, what does that do to our contour lines? Well, let's just look at what happens to c to the 3 halves if c goes from 1 to 4. Okay? 1 to the 3 halves is, of course, 1, 2 to the 3 halves is 2.8, 3 to the 3 halves is 5.1, 4 to the 3 halves is 8. So that between c equal 1 and 2, our c to the 3 halves, which is the factor that tells us how big our ellipse is, increases by 1.8. Between c equals 2 and c equals 3, it increases by 2.3, and between c equals 3 and 4, it increases by 2.9, factor 2.9. So the ellipses are not just getting bigger, they're getting bigger faster. So we have something that might look like this. Here's our c equals 1 ellipse. Okay, our c equals 2 ellipse is already 2.8 times the, I don't want to say diameter, but I'm going to, the semi-axes are 2.8 times as great as this. And then when we get out to c equals 3, they're 5.1 times as great as this. Okay, so they're growing, but the spacing here keeps increasing. Looking at the spacing on the x-axis from here to here, and then a bigger gap here. What does that tell you? It tells you that the graph is getting less steep. If we look at the xz plane, the xz intersection, with this surface, we get z cubed equals 2x squared, and of course in the xz plane y is 0, meaning that z is the cube root of 2 times x to the 3 halves. Okay, well, that gives us this. Without even using that function, though, we can see what's going to happen, because for c equals 1, here's your semi-axis in the x, actually I say this could be the x or the y, xz or yz plane. Okay, if this is your semi-axis for c equals 1, the semi-axis grows by the time you get to c equals 2, and more than doubles, and then the difference in the semi-axis from c equals 2 to c equals 3 is greater than that between c equals 1 and c equals 2, so this is, the semi-axes are not just getting bigger, they're getting bigger faster and faster, giving you a downward concavity here. Okay, so this is a picture of what? It's a picture of not a paraboloid, not a cone, but a surface that's flaring out, kind of like the, yeah, there's a word for the end of a horn, okay? That kind of a horn-shaped figure. And that's what you get by looking at the contours of this function. And there's a little blurb down here as a quadratic surface. We see that okay, this note, elliptical cone, never mind, that's right, okay. So this is just an explanation of this as a quadratic surface looking in the xz plane and so forth. We conclude that this surface is an elliptical cone. Okay, so here we've got, as z goes up, as we move away from the origin, z goes up faster and faster for this one. Here, z goes up at a constant rate, giving us a cone. Here, z goes up more and more slowly, giving us a flared out type surface. So we're going from this to this to this. Hopefully that's somewhat clear. But if you think about this analysis and about the level surfaces, the contours, it'll become much more clear. And the whole method of contours follows this pattern. We don't always have cones, we don't always have ellipses. Sometimes the surfaces get very complicated, but very often we can map out the contours and get a picture of what the surface looks like.